fact, I don't have a pointer with me, but it's basically if you kind of look in behind the primary mirror, sort of in this area here, that's where the fine guidance sensor hardware is located. But it's basically responsible for pointing the telescope and keeping it pointed on targets as it's looking at stars. And, so it's a pretty important piece of hardware. Without it, this telescope would essentially not be able to do its mission. So pretty important contribution to the program. So it's an international program. Canada's contributing, as well as a couple other countries, I think. US, of course, NASA being the prime contractor. So there's two main elements to that, the guider and the tunable filter imager that ComDev Ottawa is working on. And they're getting close to completing that program now. So they delivered something called the engineering test unit to the NASA Goddard Space Flight Center in September last year. And they're now completing testing on the flight model, which will be delivered probably sometime early this fall. So it's completing testing right now at the David Florida Lab in Ottawa. Also doing something called Sapphire, which I don't know if anybody's heard about, but that's a mission for the Canadian Department of National Defence under the Defence Research and Development Canada branch in Ottawa, also located near the David Florida Lab. And it's a surveillance of space mission. So it's basically looking at objects in low Earth orbit. And that is scheduled to be launched from India on a PSLV rocket next year, middle of next year. And so right now it's in system testing. We're supplying the payload essentially for this spacecraft. It's a small satellite, a couple hundred, 150 kilograms in size. We're also completing a program called CEFI, which is the Canadian Electric Field Instrument. It's a contribution to ESA's SWARM satellite constellation, and it's for mapping the electric field, the ionosphere, in Earth orbit. So there's 3 flight models to be delivered there. The first one has already been delivered, and the second and third models will be delivered soon. And launch for that one as well is middle of next year. We're also supplying the central electronics for the RadarSat constellation mission, which is a constellation of 3 RadarSat satellites that MDA is the prime contractor for. So it's one of the big programs we're working on right now, and that'll be delivered in 2013. So we also have a capability in our Ottawa facility for manufacturing solar panels. So this is something that this was a company that we acquired actually in Ottawa a couple of years ago. Not sure if anybody has heard of the company called Roots Astro Engineering. They were a small company that specialized in solar cell laying down on panels, as well as some other specialized harnessing capability. So ComDev acquired that company about a year and a half ago. So we've integrated that now into our operations, and that's really good actually for our microsatellite group, because they're supplying the solar panels for our, one of our missions that I'll talk about a bit later. So another kind of interesting thing that we're involved in, along with the University of Guelph, is advanced life support systems. So looking at how, for planetary exploration missions, how are we going to be able to create closed-loop life support systems that can sustain themselves without constant input, essentially, from Earth. So this is research that's been going on at Guelph for a couple of years now. So we have a supported research chair there that we fund to continue this research. It's kind of neat too, because it also has some applicability for for ground-based applications like remote northern communities in Canada. So, kind of interesting. Okay, so now on to the main subject of my talk, which is the Mission Development Group. So this is a group that was established in Cambridge about 5 years ago now, to specifically look at what we call microspace solutions. And what I mean by that is basically low-cost, small satellite type solutions for specific problems. Most of our company works on really, really, really big, expensive missions that take many, many years and many hundreds of millions of dollars to fly. So we're looking at the complete opposite end of the scale in this case. We're looking at missions that you can develop within a matter of months to maybe a couple of years, with total budgets of somewhere on the order of a few $1 million, not hundreds of millions of dollars. Something you can rapidly build and test and launch. So we now have a dedicated facility for that in Cambridge. We have engineering offices, we have a development lab where we can quickly prototype hardware. We've got a full spacecraft assembly lab there. And we also have a mission operations center that we can actually operate command and control spacecraft out of that facility. So the capabilities that we have in the Mission Development Group include things like mission design and analysis, so looking at orbital mechanics, you're looking at coverage, operating scenarios, system engineering. We've been designing a spacecraft bus, a microsatellite spacecraft bus, payloads as well, unit and spacecraft assembly, integration and testing, all in that facility, and mission operations, like I mentioned. So the first main sort of problem that we chose to tackle, and kind of the primary reason why the Mission Development Group was formed, was an opportunity we saw in something called AIS, which is the Automatic Identification System. And what this is a system that maritime vessels use, so ships, to communicate with each other and with shore-based stations. And it's essentially, it's a system that was developed by the International Maritime Organization, and it's now mandated to be used on all commercial ships, essentially for the purpose of collision avoidance. But it's a system where the ships broadcast their identification, their position, their course, their speed, and there are other bits of information they can include as well, like cargo information and that kind of thing. It was designed for line of sight on the surface of the Earth, and it uses a self-organized TDMA communications architecture. So within roughly 40 nautical mile cells, each of the ships within that cell organize their communications so that they all know when to broadcast and when to listen for other broadcasts. And all of that's just within one cell, and then there are, numerous cells sort of all over the place. So this was never designed to be received from space, never designed as a space system. But as a ground-based system, it's quite limited because if you're a country, say, that's trying to monitor your coastline, you can have a bunch of these AIS base stations along the coast. But you'll only be able to see out about 40 nautical miles, which in nautical terms isn't very far. So as soon as there are ships outside of that range, you don't know that they're there or where they are, or if they're approaching your coastline. So there was an opportunity here to look at, is it possible, first of all, to look at this from a space perspective and if we can do that, what benefits would that get us? So